In this video, we are asked to show that this integral is equals to pi times the ln of a plus b over 2, right? So we are going to start off with an identity that will make everybody happy. Cosine square of x can be replaced with 1 minus the sine square of x. That is from the Pythagorean identities. Let's replace that in our integral. I is the integral from 0 to pi over 2 of the ln of a squared times sine square of x, and this is added to b squared, and in place of cosine square of x I'm going to put 1 minus sine square of x, like this, dx. I is equal to the integral from 0 to pi over 2 of the ln of this is now a squared sine square of x, right, minus b squared, right, sine square of x, and then plus b squared, like this, and then dx. Alright, so far so good. I is the integral from 0 to pi over 2 of the ln of, now I'm going to factorize sine square of x out, and that's going to be left with a squared minus b squared, all this one multiplied by the sine square of x plus b squared dx. Alright, so from here what I can do is to factorize b squared out in the ln. So the ln of, I am going to factorize b squared out, and when I do that, what is left here is 1, and then what is left here is a squared minus b squared all over b squared, and this is multiplied by the sine square of x, like this, dx. Alright, so now permit me to, I'm just going to call this one a squared minus b squared all over b squared. This one is a constant. Permit me to call it k. That is this one. And then if I using the laws of logarithm, the ln of a times b is the same as the ln of a plus the ln of b, like this. So using the laws of logarithm and calling that k, that is going to be the integral from 0 to pi over 2. This is now b squared multiplied by the whole of this. So that is going to be the ln of b squared plus the ln of 1 plus this one, which is now k, so which is k times sine square of x, like this, and all this one dx. Alright, so now let's split this one into two different integrals. This one, using the power rule of logarithm, that can be written as this: the integral from 0 to pi over 2 of 2 times the ln of b, alright, and then dx, plus the integral from 0 to pi over 2 of the ln of 1 plus k times sine square of x, and then dx. These are the two different integrals. Integrating this one is just x times this constant, because this is a constant in the x world. So if we have that, integrating is x, and then putting in the limit will be pi over 2, right? So integrating the whole of this is going to be 2 times the ln of b, which is multiplied by the limit pi over 2 minus 0, which is pi over 2, plus the integral from 0 to pi over 2 of the ln of 1 plus k times sine square of x, and then dx. So this 2 will cancel this 2, right? This will cancel this peacefully, and now what you are left is this. So you have I to be equal to pi times the ln of b, or ln of b times pi, like this, plus the integral from 0 to pi over 2 of the ln of 1 plus k times sine square of x, and then dx. So next task is to solve this. So permit me to call this one equation star. Now let's tackle this one. Let's call this one integral I of k, right? Let me switch colors. I of k is equal to the integral from 0 to pi over 2 of the ln of 1 plus k times sine square of x, and then dx. Alright, cool. Now let's solve this. We are going to solve this one using what we call the Feynman's, right? Feynman's technique or trick. That is the differentiation under the integration sign. So to integrate this, I have to differentiate the left hand side with respect to the parameter, which is k here, right? And I'll do the same thing to the right hand side. So that is the partial derivative with respect to k of the ln of 1 plus k times sine square of x, and then dx. Alright, so the left hand side will be I prime of k, that is the derivative, then the integral from 0 to pi over 2. Now differentiating this one with respect to k, that is going to be 1 all over 1 plus k times sine square of x, and then I will differentiate this with respect to k and multiply, which is sine square of x, and then dx. Alright, so this is the same as the integral from 0 to pi over 2 of sine square of x, right, all over k sine square of x, and then plus 1, right, dx. So this is what we have. Now I'm going to manipulate this integral. So this integral permits me to multiply the numerator by k. When I do that, I have to nullify the effect by multiplying the integral by 1 over k, right? Next is to add 1 to the numerator and subtract 1 to the numerator. And when I do that, the integral now looks like this. I have I prime of k. This is equal to 1 over k is a constant in the x world. The integral from 0 to pi over 2 of, we have k sine square of x plus 1. That is grouping the first two terms into 1 all over the denominator, which is k sine square of x plus 1, and then dx. And the next integral is going to be minus 1 over k, the integral from 0 to pi over 2 of 1 all over k sine square of x plus 1 dx. Alright, cool. Now you see that the first integral, these ones will cancel out peacefully. And then this is what you have. You have I prime of k, and this is equals to 1 over k, and then you are integrating 1 in the x world, like this, minus 1 over k, and the integral from 0 to pi over 2 of 1 all over k sine square of x plus 1 dx. Alright, so integrating 1 in the x world is x, and you put in the limit, that's going to be pi over 2. So this one will evaluate to pi over 2, right? So that is going to be I prime of k, and that is equals to 1 over k times pi over 2. So pi over 2 times 1 over k is pi all over 2k. Then minus 1 over k, the integral from 0 to pi over 2 of 1 all over k sine square of x plus 1 dx. So permit me to call this one equation double star. Alright, because we'll have to come back to it later on. So now I am going to solve this integral. I'm going to call this integral I1, right? So this integral I1 is equal to the integral from 0 to pi over 2 of 1 all over k times the sine square of x plus 1 dx. Now let's solve this one. In solving this is what we have. We are going to do a substitution. Let me switch colors. So in doing the substitution, we are going to let let's say y to be equal to the tangent of x, right? When we do that, what will be the change in limits? When x is equal to 0, y is going to be equal to 0, that is tan of 0. And when x is equal to pi over 2, y is going to be tan of pi over 2, which is infinity. So the limits will change from 0 to infinity. And now what about an expression for dx? So from our substitution, we can write x as the tan inverse of y, right? And dx is going to be equal to 1 all over 1 plus y squared dy. So we have an expression for dx. Now what about sine of x? So sine of x, I'm just going to draw a right triangle here and demonstrate that. So y over 1 is equal to the tangent of x. That is a substitution. So our angle here is x. So tan of x is opposite, which is here, over adjacent, which is here. And the hypotenuse, the line opposite to the right angle, is equal to the square root of the sum of squares of the other sides, right? So the square root of y squared plus 1 squared. And now we can find sine of x from here. So sine of x is equal to opposite, which is y over hypotenuse, the square root of y squared plus 1. So if we want sine square of x, we can just square both sides. And that is going to be y squared all over y squared plus 1. So this is sine square of x that I can replace in our integral. Now let's take the integral into the y world. I1 is going to be, the integral will now change from 0 to infinity. Those are the limits of integration. And now we have 1 all over k times sine square of x, which is this, right? So which is k times y squared all over y squared plus 1, and then plus 1 times dx, and dx is that is 1 all over 1 plus y squared dy. Alright, I1 is the integral from 0 to infinity of 1 all over, so we have ky squared plus y squared plus 1, right? All this one is divided by 1 plus y squared. This is multiplied by 1 all over 1 plus y squared dy. And we see that these ones will cancel out, right? So they'll cancel out, and what you are left is this. I1 is equals to the integral from 0 to infinity of 1 all over, the denominator can now be written as k plus 1, like this. All this one is multiplied by y squared plus 1, and then dy. So let's factorize k plus 1 at the bottom out. When we do that, you are going to be left with y squared plus 1 all over k plus 1, like this, and then dy. Alright, I sub 1 is going to be equal to 1 over k plus 1 is a constant in the y world. Then the integral from 0 to infinity of 1 all over y squared plus, this can be written as 1 all over the square root of k plus 1, all this one squared, and then dy. And now comparing this one to the arctan integral, you have the integral of 1 all over x squared plus a squared dx. This is the same as 1 over a times the arctan of x over a, like this. So now let's use that to solve this integral. I1 is equals to 1 over k plus 1, and then solving this is 1 all over this. A here is now 1 over the square root of k plus 1, like this. And then we are going to have the tan inverse, or the arctan of y all over a, 1 over the square root of k plus 1, the limits of integration from 0 to infinity. Now this one times the reciprocal, that is going to be equal to what? This is going to be the square root of k plus 1 over k plus 1. And then we are going to take the limit as y approaches infinity of the tan inverse of the square root of k plus 1 times y, minus plugging in 0 as the lower limit. Tan inverse of 0 is 0, right? So this one, I1 is going to be what? So we can rationalize the radical. When we do that, that is going to be 1 all over the square root of k plus 1, like this. And then as y is approaching infinity, this is infinity, and tan inverse of infinity is pi over 2. So this is equals to pi all over 2 times the square root of k plus 1. This is what I1 is simplifying to. Now that we have I1, we can go back to equation double star, right? That is from here, equation double star, right? So that is equals to, equation double star is I prime of k is equals to pi over 2k. So I prime of k is equals to pi over 2k minus 1 over k times equation I1. If we can go back, so I prime of k is pi over 2k minus 1 over k times I1. So pi over 2k minus 1 over k times I1, and I1 is this, right? So this is equals to pi over 2k minus 1 over k multiplied by I1 is pi all over 2 times the square root of k plus 1. This is I prime of k. Alright, I prime of k is equal to, so we see that pi over 2 is a constant, right? So pi over 2 can pull that one out, and I'm left with 1 over k minus 1 all over k times the square root of k plus 1, like this. So now this is what I have, but I don't want I prime of k, I want I of k. So what I can do is to integrate with respect to k, right? So to take the antiderivative, so I have the integral of the I prime of k with respect to the parameter k, and this is the same as pi over 2. Then I'm going to integrate with respect to k of 1 over k minus 1 all over k times the square root of k plus 1. All this one decay. So integrating this one is I of k, which I want, and now I have pi over 2, and then integrating 1 over k in the k world is the ln of k, right, minus the integral of 1 all over k times the square root of k plus 1 decay. How do I integrate the second one here, this one? So here, permit me again, I am going to solve this one doing a trig sub, right? The substitution I'm going to use, I am going to let k to be equal to the cotangent square of theta, right? And when I do that, decay is going to be equal to what? This is going to be 2 cotangent of theta, and then I'm going to multiply by the derivative of the cotangent of theta, which is negative cosecant square of theta, like this, and then the theta. So in place of decay, I'm going to put in negative 2 times the cotangent of theta, cosecant square of theta, the theta, right? So now let's take the integral into the theta world. So I have I of k, and that is equal to pi over 2. This is multiplied by the ln of k minus the integral of 1 all over k is the cotangent square of theta times the square root of k squared. So square root of k, which is the cotangent square of theta plus 1, and this is multiplied by decay, and decay is negative 2 cotangent of theta cosecant square of theta d theta, like this. Alright, so we know that this one, cotangent square of theta plus 1, is the same as the cosecant square of theta. So I can just replace this one with the cosecant square of theta, right? Alright, so I have I of k, and that is going to be equal to pi over 2. This is closed with a square bracket. Pi over 2 multiplied by the ln of k minus the integral of 1. And we see that this cotangent of theta is going to cancel 1 cotangent of theta, right? And we have this 2. This 2 is going to come out of the integral sign because it's a constant, this one, and you have negative and negative, which will become positive 2, right? So we are going to have positive 2 in front here, and now what is left on top is the cosecant square of theta d theta, and this is divided by cotangent of theta is left here, right? And then this is multiplied by the square root of this one is cosecant square of theta, and that is from the Pythagorean identities. So this is the cosecant square of theta, like this. Alright, so I of k, this is equals to pi over 2, right? So we have the ln of k plus 2 times the integral of the cosecant square of theta d theta divided by, this is the cotangent of theta, and this is multiplied by the square root of the cosecant square of theta is the cosecant of theta, like this. And we see that this one is going to cancel 1 on top, and now what we are left with is this. This is equal to pi over 2 times the ln of k plus 2 times the integral of the cosecant of theta all over the cotangent of theta d theta. Alright, so I of k, this is equals to pi over 2, right? And then we have the ln of k plus 2 times the integral. Cosecant of theta is 1 over sine of theta, right? And cotangent of theta is the cosine of theta all over the sine of theta d theta. And now when you multiply top and bottom by the sine of theta, this is what you have. So I of k is pi over 2. This is multiplied by the ln of k plus 2 times, multiplying top and bottom by sine of theta is going to be 1 over the cosine of theta d theta. and this is equals to pi over 2 multiplied by the ln of k, right, plus 2 times the integral of the secant of theta d theta. So integrating secant of theta, we have done this before severally. So this is pi over 2 and then ln of k, and then plus 2 times integrating secant of theta is the ln of the secant of theta plus the tangent of theta. I can put that in absolute value. So we are done with the integration. Put the constant of integration c. Alright, so now let's move back into the k world. So initially we know that k is equals to the square root of the cotangent of theta, right? So let's go back to our substitution. So we know that k is the cotangent square of theta, right? So that implies that the square root of k is equals to the cotangent of theta, right? So that is the same as the square root of k over 1, like this. And now we have this. We can draw a right triangle, right? So our angle here theta, our right angle is here. Cotangent of theta is adjacent over opposite. So the adjacent is here, which is square root of k, and this is opposite 1. So the hypotenuse is always the square root of the sum of squares of the other two sides. So the sum of squares of the other two sides is 1 squared is 1 plus the square of root k is k. So this is what we have. Now we can find secant of theta and tangent of theta in terms of k. So secant of theta is equal to secant of theta is hypotenuse, which is the square root of 1 plus k all over adjacent, which is the square root of k. And then the tangent of theta is opposite over adjacent, which is 1 over adjacent, the square root of k. So now we can take the integral into the k world entirely. So I of k is pi over 2, and this is multiplied by the ln of k plus 2 times the ln of secant of theta is the square root of 1 plus k all over the square root of k plus tangent of theta is 1 over the square root of k plus the constant of integration. I of k is equal to pi over 2 ln of k, right, plus 2 times the integral 2 times the ln of this, which is 1 plus the square root of 1 plus k all over the square root of k, like this, plus the constant of integration. Now let's apply some laws of logarithm. That is pi over 2 multiplied by the ln of k plus 2 times the ln of 1 plus the square root of 1 plus k, and then minus 2 times the ln of the square root of k, like this, plus the constant of integration. Applying laws of logarithm here. And now we see that this one is the same as, so we have the ln of the square root of k. This is the same as the ln of k raised to the power 1/2. So if you have 2 multiplying that, so this 2 times the ln of the square root of k is the same as ln of k, because this 2, which is a power, will multiply this 2 in front, right? So this one is the same as the ln of k. So I'm just going to replace that with the ln of k, like this. So I'm going to replace that with the ln of k minus the ln of k plus the constant of integration. And we see that this one is going to cancel this one beautifully. And now I of k is equal to pi over 2, and then this is multiplied by 2 times the ln of 1 plus the square root of k, 1 plus k, plus the constant of integration. So I of k is equals to pi times the ln of 1 plus the square root of 1 plus k plus the constant of integration. So now how do you find c, right, the constant? We can put k is equals to 0. So when k is equals to 0, you have I of 0 to be equal to pi times the ln of 1 plus the square root of 1 plus 0, which is 1, and then plus the constant of integration. I of 0 is equals to pi, and this is multiplied by the ln of 2 plus the constant of integration. But what is I of 0? So when we go to where we started working with I of k, right? So when we go to I of k, this is I of k. So I of k here, when we plug in k to be equal to 0, when k is equal to 0 here, everything here goes to 0. Then you have the ln of 1, which is equal to 0. So I of 0 is equal to 0, right? So we just go down there and replace I of 0 with 0. All right. So I of 0 is 0, which is equals to pi times the ln of 2 plus c. And then c is equal to negative pi times the ln of 2, like this. So now that we have c, we can go back to ik and then replace it. So we are going to have pi times the ln of 1 plus the square root of 1 plus k, and then plus c. And c is negative pi times the ln of 2. Alright, so this we can factorize pi out, and that is ln of 1 plus the square root of 1 plus k, right, minus the ln of 2. And now applying laws of logarithm, I of k is going to be equal to pi, and then you have the ln of 1 plus the square root of 1 plus k all over 2, like this. So this is I of k. Now remember, the original integral is in terms of a and b. If we can recall what k is, right, so we can now finish off the integral with what we represented k with. If we can recall, we let a squared minus b squared over b squared to be equal to k, right? So we are going back to this one to finish off with our integral. So k is a squared minus b squared over b squared, right? So now let's replace k with that, and then we are done with the integral. And now here, let me wrap it up with the right pen. So now we can recall k is equals to a squared minus b squared all over b squared. This is the same as a squared over b squared minus b squared over b squared, which is 1. So now what about 1 plus k? That is just adding 1 to both sides, right? A squared over b squared plus 1, and then minus 1. That is just adding 1 to both sides. And now when we do that, 1 plus k is equals to a squared over b squared. What about the square root of 1 plus k? So the square root of 1 plus k is equals to the square root of a squared over b squared, and this is a over b. So the square root of 1 plus k is just a over b. So now let's replace that. I of k, so now it's just I, because it's now going to be in terms of a and b. So I is going to be pi times the ln of 1 plus the square root of 1 plus k. So square root of 1 plus k can be replaced with a over b, and all this 1 over 2, like this. That is what we have here. Now let's simplify this one. Alright, so we have this is I, this is going to be pi multiplied by the ln of a plus b all over 2b, like this. So this is what we have. And now if we can recall again for the last time, before we started using the Feynman trick, if we can recall, equation star is the same as ln of b times pi plus I of k, right? So ln of b times star times pi times I plus I of k. So we are going back to equation star to now finish off with the integral. So we just have to add ln of b times pi to what we got down there, and now we can wrap up the video. Okay, so the integral I, so permit me, this one is I of k. If I can call it like that, I of k, because k is in terms of a and b. All right, so I is going to be the ln of b times pi, and this is added to I of k, and I of k is pi times the ln of a plus b all over 2b, like this. Okay, cool. So now here, what do we have? So we are going to have I to be equal to the ln of b. So pi times the ln of b plus this is pi times the, so this one can be written as the ln of a plus b all over 2, right? And this one is multiplied by 1 over b, like this. I is going to be equal to pi times the ln of b plus pi times the ln of a plus b all over 2, and then that is going to be plus pi times the ln of 1 over b, right? That is using the laws of logarithm. This one is multiplying this, so that is what we have. So we have I to be equal to pi times the ln of b plus pi times the ln of a plus b over 2. And then this one is minus pi times the ln of b, because pi of 1 over b is pi of negative b, which is multiplied by pi. And you see that this one will cancel out with this one. And now, ladies and gentlemen, what you are left with is the proof. Pi times the ln of a plus b over 2, like this. And this one is the proof that we are tasked to show. So about 30 minutes of integrating this. So this integral entails, and I think it is worth it, right? So that is how I integrated this. I used the Feynman's trick to be able to solve the parameter dependent integral, right? So if you really find this video helpful, if you learned something new today, please give me a thumbs up and subscribe to my channel by supporting my channel so that I'll continue uploading engaging tutorials on integrals. I thank you so much for watching this video, and then I'll see you in the next one. Bye bye.